name is V.Naga Lakshmi from the Department of Statistics. Now I am going to explain generating functions in Unit-3. We have moment generating function which is known as M.G.F, and characteristic function C.F, and cumulant generating function C.G.F, and probability generating function P.G.F. Let's have a look on moment generating function. So the M.G.F of a random variable x is denoted by mxt and is defined as mxt equals to expectation of e power tx. We can write as summation in e power tx into probability of x if x is discrete, and integrate minus infinity to plus infinity e power tx into f of x dx if x is continuous random variable. So we can classify it as mxt equals to expectation of etx. We know that expectation of x is equals to the expansion of e power x is equals to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. We can substitute e power tx as expectation of 1 plus tx plus t into tx whole square by 2 factorial plus tx cube by 3 factorial and so on. We can write as expectation of 1 plus t, which is constant, expectation of x plus t square by 2 factorial, which is constant, we can write here, and we can apply expectation only for variable expectation of x square plus t cube by 3 factorial into expectation of x cube and so on. The moments through M.G.F can be derived as derivative of rth moment. We can derive rth moment by using this dr into mxt by dtr where t equals to 0. Properties of M.G.F. So the first property is mcx of t is equals to mx of ct. We know the M.G.F mxt is equals to expectation of e power tx. This can be write as, let us consider mcx of t that equals to expectation of e power, we write here x as cx, that equals to expectation of e power tc into x. We can write this as mx of ct or tc. Additive property. Statement: M.G.F of sum of n independent random variables is equal to the product of their respective or corresponding M.G.Fs. That is, m of x1 plus x2 plus xn is the sum of n independent random variables of t is equals to mx1 of t into mx2 of t into and so on mxn of t. Proof: we know that the moment generating function we can define as expectation of e power tx. Let's consider moment generating function of sum of n independent random variables. We can write here, and that equals to expectation of e power t into x1 plus x2 plus and so on xn. That equals to expectation of e power t into x1 into e power tx2 and so on e power txn. That equals to, we can write this term as we can applying expectation for the individual terms. So we can write expectation of e power tx1 into expectation of e power tx2 and so on expectation of e power txn. So this is the formula for mx1 of t, and this is the formula for mx2 of t and so on. This is the formula for mxn of t. Hence proved additive property. Effect of change of origin and scale of M.G.F. Statement: M.G.F is not independent of change of both the origin and scale. Proof: let's consider u as x minus a by h. We know that mxt is defined as expectation of e power tx. Consider mu of t that equals to expectation of e power tu. We can write in place of u x minus a by h. So that equals to expectation of e power t into x minus a by h. This can be further, we can write as expectation of e power t into x by h into e power t into minus a by h. So we know that this is a constant term. We write it here. e power t into minus a by h, and we are only applying for the variable to expectation. So expectation of e power t into x by h. So we know that the formula for mxt equals to e power expectation of e power tx. So this is the form at mxt. So we can write the constant term below and mx of t by h. Hence the MGF is not independent of both the origin and scale. So the next generating function is characteristic function. The CF of a random variable x is denoted by phi xt and is defined as phi xt equals to expectation of e power itx, and this can be defined as summation e power itx into p of x if x is discrete random variable, and integrate minus infinity to plus infinity e power itx of f of x dx if x is a continuous random variable. We can further define this as phi x of t is equals to expectation of e power itx. We know that again the expansion of e power x is equals to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. We can substitute this as here. So expectation of 1 plus itx square by 2 factorial plus itx cube by 3 factorial and so on. So we can further define this term as expectation of 1 plus it is constant, we write it here, and expectation of x plus I square t square is a constant term, so we write it here, and expectation of x square plus I cube t cube by 3 factorial into expectation of x cube and so on. Further we can generate moments through CF by using the formula for the rth term, which means for mu r dash is equals to I power r into dr phi xt by dt r when t equals to 0. Cumulant generating function. The CGF of a random variable is denoted by kxt and is defined as kxt equals to logarithm of mxt. So log, we know that mxt equals to expectation of e power tx, so we write it here, and log mxt we know the simplification of e power expectation of e power tx, we write it here, and so kxt is equals to k1 of t plus k2 t square by 2 factorial plus k3 t cube by t cube by 3 factorial and so on, where k1 means mean and k2 is a variance and k3 is known as mu3 and k4 equals to mu4 minus 3k2 square. We can find the moments by using these formulas. Probability generating function. The P.G.F of a random variable is denoted by Px of s and is defined as Px of s is equals to expectation of x power x. So summation, we can write it as summation s power x into p of x if it is discrete. So we can further simplify it as s power 0 into p of 0 when x equals to 0, and s power 1 into p of 1 when x is equals to 1, and so on. For nth value we can write s power n into p of n. Thank you.